Today I'd like to take up the topic of bonding. As stated earlier, it is bonding that determines crystal structure. And we know that these are all basic things, more by way of review. And ultimately then it is the crystal structure that determines properties. So these are the important things. Bonding, we will understand, that will help us to see why atoms cluster together in certain geometrical ways to form crystal structure. And then by looking at the crystal structure and the details of the atomic structure, we can then practically predict what kind of properties we can expect from such a material. Before discussing the various types of bonds, I want to discuss first of all why bonding occurs at all. What is it that makes atoms cluster together? And fundamentally the answer is to minimize their total energy, the free energy. They want to stay at the lowest possible energy. So bonding is taking place to minimize energy. When atoms are separated from each other, they are at a higher energy state than when they have bonded. And this is the driving force that drives the atoms to cluster together to form, first of all, gases, and then as you compress them further, you form liquids and then solids. So ultimately it is minimization of energy, the total energy, that determines the bond. And if you have two atoms that are far apart, and you look at the total energy of the system, that is more than when they have bonded together to create one of the particular types of bonds that we will be looking at. There are two forces that cause bonding. And one is an attractive force, which we refer to in terms of a Coulombic interaction. There are positively charged parts of an atom which are attracting the electron cloud of the adjacent atom and vice versa. And there's also a repulsive force which is primarily due to nuclear-nuclear interaction and the overlap of the electron clouds. I will just put that briefly as electron cloud overlap. So as the atoms get closer and closer to each other, now the two nuclei which are positively charged start repelling each other. The electron clouds, both of which are negatively charged, also repel each other. So as the electron clouds overlap with each other, we get the repulsion. And therefore we can guess that the repulsive force will of necessity be a short-range force, because it is active primarily when the atoms are really close to each other. And the sum of these two forces is the resultant that determines the bond length and things like that, where the atoms finally settle together. One force that is pulling them together and one that is repelling. We can sketch for such a system a force versus distance curve. And when we do that, we see there is an attractive force that, let's say, we represent something like that. When they are really far apart, the distance here refers to the distance between the atoms. When they are really far apart, there's nothing much happening. And as you bring them closer together, the attractive force is increasing. It's a Coulombic type 1 by R interaction, right? And then there's also the repulsive force that is at work as you come really close. So one is an attractive force and the other is a repulsive force. And what we see for the atom is the resultant, which may be sketched somewhat like this. That's our resultant force. And what we observe is that there is a certain distance called the equilibrium distance, which we will denote here by R naught, where the force is 0. So if the atoms are sitting R0 apart from each other, there is no net force acting on them, and that is the bond length. So when they bond, they sit at an equilibrium distance R naught from each other. As I stated earlier, bonding occurs to minimize the energy, and so we can express the same thing in terms of energy. Then we can draw an energy versus distance curve, which we can obtain from the total force integrated over dr. Okay? And so we have the energy versus distance curve similarly drawn. And what we see is something of this nature. When they are far apart, the energy is high. As they come closer and closer together, there is a minima, and then again the energy increases as they are brought closer together, as the repulsive force takes over. And again we see that the minimum in the energy is at a distance, what we defined earlier as our equilibrium distance, R naught. So, as I said earlier, the atoms are bonding because they want to minimize the energy, and when the bond is formed, they are sitting at a distance R naught from each other, where they have a minimum in energy, which we will call E naught. Okay. This area is the attractive force, and the repulsive force at R naught from each other, they are sitting at a minima. And typically, as we will see later, this curve gives us a lot of information if we know how we might represent it for a given set of atoms. Various properties can be roughly predicted from a curve of this nature. Particularly note the depth of that curve is 1 bit, which we call E naught. That is very useful to us. The actual shape of this curve may vary depending on the particular atoms that we are looking at, but typically the overall shape will be the same. Okay, if we have ionic bonds or covalent bonds or different kinds of bonds, the actual details of the shape may be a little different, but overall there will be a minima in the energy curve at a distance R naught for the particular set of atoms. And there are various mathematical expressions that have been derived that give us approximate ideas of how to represent the attractive force and the repulsive force, which we will look at in a second. As I mentioned, let us look at this curve once again and see what all kinds of information we can get from the E versus R curve. It's rather surprising. When I first started understanding materials, this curve in particular, I think, is what drew me into material science, I would say. That the kind of simple things that you can derive from a curve of this nature is very startling almost. Let's begin with the depth of the well, the minima. I'm redrawing that for us. We have this depth. What kind of information can we get from the depth of that well? Well, for one, it tells you how much energy would be required to break the bond. In other words, what is the binding energy between these two? Or the bond strength is what it is related to. And which in itself is an indirect measure of the melting point of the material. When I melt a material, I'm going from a solid state where they're at this equilibrium distance R naught, and then the atoms have to break apart and get loose and more fluid. And so what energy will it take to break these from and separate them from each other gives us some idea of the melting point of the material. A very shallow curve probably will have a melting point that is low, and a deep curve will have a higher melting point. It can tell us also how strong is the material by similar arguments. Strong. Of course, there are other factors that determine ultimately whether a material behaves as predicted, but just at first guess, if we were to make a guess about the property, we could expect a deeper curve to have much stronger properties, higher melting point than a similar one with a shallow curve. The second thing, which is also fascinating, is the asymmetry of the curve. I'm writing that wrong. I think there's an M there. And this is related to thermal expansion. What do I mean by the asymmetry? You see, I can draw a couple of curves to illustrate my point. I drew this curve, and if you'll notice that around this minima, the curve is not symmetrical. And we saw earlier that typically the atom is sitting at its equilibrium distance, R naught here. Again, we are doing the E versus R curve. What happens to this? This is the potential energy. What happens to this when I supply heat to the material? Excuse me. Some kinetic energy is given to the material, and now this atom starts vibrating around its mean position, and its energy rises. The total energy is now at this level. And we do the same thing, higher energy, higher temperature, it gets more energy, and it vibrates between these 2 points, and so on. Now what you notice is here, that while it was sitting here, it was sitting at an average distance R naught from each other. But as the temperature has gone up, more energy is supplied to the system, the midpoint of these is gradually shifted due to the asymmetry of the curve. In other words, the average separation of these atoms, as they have risen in temperature or increased in energy, is now farther apart than the R naught at which they sat at equilibrium. And therefore, when we look at it, we say the material is expanding. Initially, all the atoms were at an average distance of about R naught apart from each other. Gradually, as the temperature goes up, their average separation is increasing, and so we say the material has expanded, and we call that thermal expansion. And the larger is this asymmetry, the larger, if you increase the asymmetry, thermal coefficient of expansion increases. TCE refers to thermal coefficient of expansion. Okay? So the more the symmetry, the smaller is the tendency to expand with temperature, the larger the asymmetry, the larger the tendency to expand. You can see how by looking at something very simple like this, how two atoms are bonded together or a group of atoms are bonded together, and we know their energy distance profile, we are able to predict different things about the material. Let's take another case, or just continuing with that for a second. What I mean by TCE, the thermal coefficient of expansion, defined as alpha, is given by 1 by delta T L minus L naught by L naught. Okay? Simply the change in length divided by the original length per unit rise in temperature, which is in its more familiar form, we express it as. So if alpha is larger, then the material length will change more for a given delta T. And alpha depends on the bond type, which actually is related to the asymmetry of this very curve. Generally speaking, metals have large alpha compared with covalently bonded materials. This is just a generalization, but that is one important thing we can understand from this curve. Another property are the moduli, bulk and elastic moduli. I'll deal with bulk modulus here, which we call K. When we apply a pressure P to the material, volume changes by delta V. And we from its original volume, which was V naught. Okay? So we express that change in terms of this equation. P is equal to minus K delta V by V naught. V naught is my original volume. Delta V is the change in volume. K is this bulk modulus that I'm talking about. And P is the applied pressure. The actual expression for K will depend on the particular kind of structure we are talking about. But for a simple cubic cell, we can write K is equal to 1 by 9 R naught D2E by dr square at R is equal to R naught. What does this tell us about the K? What is it related to in terms of my E versus R curve? What is this D2E by dr square? Curvature, right? The second derivative of my E versus R curve. How rapidly is the slope of that curve changing near the minima? So again, if I know my E versus R curve, and I'm interested in how rapidly is the slope changing around this point R naught. And simply by knowing that, I can make a prediction of how this material will respond in terms of a volume change when pressure is applied to it. So if the curvature is large, we have a higher modulus. If the curvature is small, it is a lower modulus. And one other property which is again related to this itself, the elastic modulus. Or the Young's modulus, as it's sometimes referred to. We can make a guess from the force versus distance curve. Note, I'm plotting the force versus distance curve. If you remember, the resultant force acting on the system was something like this. And what I'm talking about is that now it is sitting at an equilibrium distance, R naught, and we apply forces to this set of atoms. It may be tensile, pulling them apart, which would be in this direction, or it may be compressive, where we are trying to squish them together a little more. And what we see is that this curve is more or less linear in this region for small forces that are applied. Okay? So as I change the force that I'm applying, the separation, how they respond, the change in length is going to be linear, which is exactly what we call Hooke's law in the macroscopic world. So what we have as Hooke's law for elastic media, expressed as sigma is equal to y epsilon. That's your stress, and that's your strain, and that's your modulus, which simply says that the change in length is a linear function of the applied stress. It express it as epsilon is equal to sigma by y. And it comes simply out of the fact that around the equilibrium distance, I have a linear region. So for small changes in length, this is going to be linear, and that's what we know as Hooke's law, which can also be related to our d2e by dr square similar way if we write it in terms of the d2e by dr square. It will turn out to be something like this. You can express your stress in terms of force by area, and this as a change in length by length, and you will end up with an expression of this form, something like this. Again, we are back to the curvature. Okay? So you can see from a simple set of curves of E versus R that we can roughly have an idea about for different types of bonds, we can begin to make all kinds of predictions about how this material will possibly behave. There are many other things that would be taken into account, like defects, the history of the material, how it has been treated in different ways by, say, heat, or various things that would ultimately determine its final properties. But at a first glance, this is what we are able to understand. Looking at microscopic phenomena, namely how the atoms are arranged, bonded together, we are making guesses about the material itself. Let me take up now the different types of bonds. We sort of conveniently talk of bonds in various classifications. And the first major classification I would make is in terms of primary bonds and secondary bonds. The primary bonds are the ones that we are most familiar with and which ultimately dominate, namely covalent, ionic, and metallic. And we have the secondary bonds, which are van der Waals, hydrogen bond. And this classification is roughly based on how the valence atoms, the valence electrons distribute themselves in this collection of atoms. And depending on the description, we may say the charge is transferred from one to the other. We say it's ionic. If they're shared, we say it's covalent, and so on. We'll take up those descriptions in a second. But this is just a basic classification in terms of the primary bonds, which actually determine the structure. And then there are some secondary bonds which play other roles, and the van der Waals in particular being very important for the primary structure of inert gases when they are solids. Let's try to put some mathematical expressions in trying to look at these covalent, ionic, and metallic bonds in particular. Let us put some expressions to the repulsive energy and the attractive energies. Very often, the repulsive energy, particularly in ionic crystals and in some other kinds of bonding, can be represented by an expression of the nature B by R raised to the power 12, where B is a constant, R is the distance between the atoms, raised to the power 12. This is referred to as the Lennard-Jones potential. It turns out that the Lennard-Jones potential is basically an empirical description. What do we mean by empirical? An equation that sort of fits the observations. There isn't any deeper basis for this equation. If you plot it in terms of B by R raised to the power 12, it expresses what is observed experimentally. And B has to be determined by fitting it to the experimental observation. There's another expression, lambda exponential minus R by rho, where again lambda and rho are constants. And this is known as the Born-Meyer potential. Turns out that the Born-Meyer potential is not simply empirical, but has its basis in quantum mechanics. So these are two alternate expressions that exist for the repulsive energy. And these constants like B, lambda, and rho need to be determined for a given system by comparing it with the experimental observations. Let's take up each of the bonds in turn and look a little more at them. I begin with the ionic bond, which we all know involves the transfer of charge from one atom to the other. And when we do that, we produce what are called ions. A neutral atom losing an electron gains a positive charge. A neutral atom gaining an electron acquires a negative charge. And it is then the ions that are responsible for producing the ionic bond. These ions in an ionic bond are arranged geometrically in what we refer to as the crystal structure. And each of the positive charge is surrounded by negative charges. So they have fixed positions within their crystal structure. The positive charge is occupying some of the sites, and the negative charge is occupying other sites. And overall, excuse me, electrical neutrality is maintained. The material cannot be positively charged or negatively charged. Overall, neutrality is maintained. A simple example, if you're all familiar with, are the alkali halides, okay, the alkali group, the halogen group, and a typical example being sodium chloride, with which we are all familiar, common salt. And when we look at this, the sodium atom can be expressed, the electronic arrangement, as 1s2, 2s2, 2p6, 3s1. That is, there are 11 electrons in the sodium atom that need to be arranged around the nucleus. And what we see immediately is that if I could get rid of one electron, I would acquire a closed shell structure. Right? We just simply, if you can get rid of this one electron, then the rest of it is a closed shell structure, which is spherically symmetric and so on. And the energy that is required by sodium to get rid of this first electron is known as the first ionization energy. And in the case of sodium, it turns out to be approximately 4 to 5 electron volts. So for sodium to become a neutral sodium atom to become a sodium ion, I need about 4 to 5 electron volts to create this ion. Okay. We can do the same for chlorine also and see. So sodium will become a sodium ion and has an electron to give up. We can do the same for chlorine. And when we look at the chlorine structure, we have 17 electrons to distribute. We see that if we can have one more electron here, chlorine would have a closed shell structure. So there's a driving force for both of them, for the sodium as well as the chlorine, one to give up an electron to become more stable, one to acquire an electron to become more stable. But this costs energy. We refer to the energy required, the energy that is the electron that is attached to the chlorine is bound by as the binding energy of one electron, as the affinity, electron affinity. We call that electron affinity. Okay? And this turns out to be approximately 3 electron volts for the halogen group. And so now this chlorine acquires an electron and becomes a chlorine ion. As we see, it costs energy to create these ions. So why would they want to do that? And it turns out that once we have these two ions, one is positively charged and one is negatively charged, and there is an attractive force between them. And this more than compensates for the energy that is required to create the ions. So the expenditure of energy, how much energy we have to put in to create ions, turns out to be less than the gain or I should say the lowering, again is the wrong word to use, lowering in energy for sodium chloride. That's the driving force here. I use energy to create the ions, but when they are attracted together, I am able to minimize my energy, and the minimization that takes place compensates for this additional energy that I have to spend to create the ions. So that is what causes sodium chloride to form by combining sodium and chlorine to give me sodium chloride. In an ionic solid, for any given ion pair, all right, we have a lot of ions. If we take any particular ion, let's say a positively charged ion, and we look at the interaction with all the other ions around it, surrounding it are negative ions, but there are positive ions beyond that. So I'm not restricting. I said any. When we write an expression for the attractive potential, we find then we can express it as plus or minus E squared by 4 pi epsilon naught R I J. Any ion I interacting with the J ions around it. Not yet. I'm coming to that. Okay? Why is there the plus or minus sign? If it is interacting with a negative charge around it, the positive charge and the negative charge, or it could be, if it is oppositely charged, or whether it has the same charge. Depending on that, the sign here will be different. It's simple Coulombic attraction between these two. To take up some more of these, when they're arranged in a regular array, I told you the ionic crystals are arranged in a regular geometrical array. The total attractive energy of an ion, which we label I, in the presence of all other ions. This was for the earlier expression was for each ion pair, and now we are looking what is the total attractive energy. Can then be expressed by the sum, where J is not equal to I, of this previous expression that we obtained. Okay? So the previous expression that we had is for a particular pair of ions. So if we have a positively charged ion, we look at any particular, say a negatively charged ion sitting at this distance, and the attractive energy for this is given by this expression. And now similar to this one, there are many more ions around it, which we then sum up to obtain this expression. If we consider only the nearest neighbor interactions, I'm restricting myself to nearest neighbor interactions, because the attraction dies out with distance. As you go farther and farther away, the attractive force is weaker. So considering only nearest neighbor interactions, we could express the previous result as minus E squared m by 4 pi epsilon naught R naught, where R naught is the equilibrium distance with its nearest neighbor. And m is what is referred to as the Modulus constant. The Modulus constant varies and it depends on crystal structure. Okay? So now for an ionic bond, I have an expression for what is the attractive potential for a given ion I in the presence of all the ions J around it. We had an earlier expression for the repulsive energy expressed in terms of either the Lennard-Jones potential or the Bond-Meyer potential. And so we can now write the total potential energy of this one ion in the presence of all the other ions is simply then going to be, say, UT is equal to U attractive plus the repulsive term. And in this case, we can write that as the expression we just wrote earlier for the attractive potential, minus E squared m by 4 pi epsilon naught R naught plus lambda exponential minus R naught by rho, using the Born-Meyer expression instead of the Lennard-Jones potential. There is a Z term that comes here, which I did not write in. I just added that here. Because we are considering only nearest, the assumption we are making there in this expression is that the repulsive force is limited to the nearest neighbors 2. And the Z number there is what is known as coordination number. You may be familiar with that. Okay? So when we restrict the repulsive force component to simply the nearest neighbors, there are Z nearest neighbors. There are Z ions near it, and therefore we introduce that term Z in this equation. You can write it in a different form simply by clubbing the Z and the lambda together, and it is sometimes expressed in those terms. B exponential minus R naught by rho. Okay. Again, this B and rho are determined from experiment. We can look at experiments, values like bulk modulus and things like that, and then come back and try to fit these data. It is also possible, if you want to express it in terms of the Lennard-Jones potentials, to use parameters. So sometimes you may see expressions like this also. R to the power n and R to the power m. Again, the attractive force component and the repulsive force, and you got A, B, n, and m as constants. Okay. But the more common expression for the ionic bonds is either this one or this expression. So we are able to now mathematically draw the U versus R, or E versus R, U and E being equivalent, the energy versus distance curve for an ionic bond, compare it with experimental data, fit these parameters, and then now I can begin to look at values of, say, d2E by dr square. I have an actual curve, and we can look at a little bit, get a little better idea of what we might expect for a material that behaves in this fashion. And what we see, what I would call the characteristics of a particular type of bond, they are very strong. So these ionic bonds are strong, typically high melting points compared to metals. They are soluble in polar liquids. An example of a polar liquid being water. Electrically, they are often insulators. The exception being in the molten state. So if you liquefy, say, sodium chloride, you get molten, you melt it. Now the ions are free, and you have ionic conduction rather than electronic conduction. Ions themselves can respond to the field. And they are rather stable chemically and mechanically. we can look at covalent bonds. And it's predominant in organic materials. But we also see it in inorganic materials, carbon, the very familiar and precious diamond, common semiconductor like silicon, germanium. These have covalent bonding. And basically the idea here is that electrons are shared between pairs of atoms to produce the covalent bond. Say, for example, in carbon, there are 4 valence electrons. So we write that as 1s2, 2s2, 2p2. And it turns out that there's not much of a difference between the 2s and 2p in terms of energy. So they're close in energy level. And so what the atom does is what is called producing an sp3 hybridized bond. We've probably dealt with this somewhere or the other, right? So 4 bonds are created of equal energy. They are degenerate, that means they have equal energy. So instead of having 2 levels like this, the S and the P, we now have 4 bonds that are referred to as the hybridized sp3 bond. And now these bonds want to stay as far apart from each other. Okay, they mutually repel each other, and they end up forming a sort of tetrahedral structure. Okay, and the angle between the bonds, if I am not mistaken, is something like this. Because all 4 of them repel each other in space and symmetrically around, and so they end up having this sort of a structure. And this is what gives diamond or some of the other silicon its particular structure, this tetrahedral characteristic. We can write the characteristics of covalent bonding as that they are brittle, and we can relate it to its structure. You see, the covalent bond is very, very directional. They are fixed in space. They want to be 109 degrees or so apart from each other. And when you try to play with it to move the atoms with respect to each other, they don't give very easily, so the materials tend to be brittle. They're very strong as a consequence too. High melting point. Hard, as is obvious. Diamond is the hardest material that is known to us. Usually insulators. Now remember, our course is fundamentally about electronic materials, and we will see that the term insulator, conductor, and so on undergo a change. People are defining it in different terms, but right now we'll just say they are usually insulators. Diamond is nowadays referred to actually as a wide band gap semiconductor. The definition has slightly changed because at higher temperatures it is no longer an insulator. So if you're trying to make use of diamond at high temperatures, it begins to behave like a semiconductor. So this standard definition, calling something a conductor or a semiconductor or an insulator, is something that depends on the particular application and the environment it is in. But for a simple definition, we can keep it here. Let's look at metallic bonds. In this case, the outermost electrons are shared between all the atoms. In other words, these electrons are delocalized. They are not bound and kept in one place. It's as if the sharing is between all these atoms. Previously, in the covalent case, we shared between 2 atoms. The electrons were more or less localized. In this case now, the electrons are shared between all the cores. And the characteristics that we have are ductile. Okay. Since they're not strongly bound, there's no directionality. Soft. Ductile means you can pull them easily. Soft. They're thermally and electrically conducting. There's lots of free electrons that can conduct electricity, and they also play a role when there's a temperature gradient. The electrons can respond and diffuse, giving you a temperature gradient. Here's another interesting property, which I didn't talk about earlier. They're opaque. We will see later on in the course that the reason why the metals are opaque is there's a lot of these free electrons. Again, it's related to the electronic structure. When light falls on a metal, it can easily absorb that light because these electrons get transferred to higher energy, and therefore they don't either transmit light or reflect much of a light, and therefore metals are opaque. So that sort of takes care of the primary bonding. I will not go into much detail with the secondary bonding, other than to say that van der Waals bonding is very important when we talk of inert gases, which are solids at very low temperatures. And in their case, we can express the total energy as A minus A by R to the power 6 plus B by R to the power 12. Basically, even though they are neutral atoms, temporary fluctuations of charge are taking place to create dipoles. There's no permanent dipoles in this case, let's say in the inert gases. They're neutral, closed shells. But as the charges move around temporarily, there is areas that are created where one part is more positive than the other, and then they bond. So in terms of characteristics, which is where we leave this topic, we can obviously guess they are weak bonds, and so low melting points, small heat of vaporization, they're transparent. Because they're closed shells, it takes a lot of energy to move an electron, pull an electron out of there, and that is what causes the absorption, and so they are transparent typically. One last thought, we define everything so nicely and cleanly, but in many real materials, it's actually mixed bonding. For example, gallium arsenide, which is a semiconductor, a compound semiconductor, it's not purely covalent, nor is it purely ionic, but it is actually a mixture of these two. And with that, we conclude the topic of bonding, and we will take up the material later, where we look at bands and how band structure is developed in these materials. Thank you.